So now we're going to look at what a Cauchy sequence is. So if I have a sequence xn in a metric space X, it is said to be Cauchy if for every epsilon greater than 0, there exists a natural number n which depends upon this epsilon, such that the distance between the mth and nth term of the sequence is less than epsilon for every value of m comma n greater than n. I know it's a lot to unpack, so let us look at an example and then think of it. So this is my sequence xn. It's represented as 1 by n. So the different terms of the sequence are 1, 1 by 2, 1 by 3, 1 by 99, 1 by 100. And it's defined on the metric space open 0, closed 1. So in this sequence, in this Cauchy sequence, if you give me any value of epsilon, say you give me an epsilon value 0.01, then I can find indices m and n in my sequence xi such that, so what are these indices m and n? These indices m and n are xm and xn. These are elements at indices m and n. So again, you give me any number, any value of epsilon as small as you want, I can find you two elements of the sequence xm and xn such that this thing is less than epsilon. That is the basic idea behind Cauchy sequences, that no matter what value of epsilon you give me, say, then I can find indices here and here. So in this case, if you take the indices 99 and 100 and you subtract them, you get something like 0.00010. So yeah, you gave me an epsilon and I can say that, okay, starting from this index, every term that comes after it, the difference between these two corresponding terms would be less than epsilon. Now, the next idea that I want to talk about is about a complete metric space. So, if I have any metric space, or say any norm space, and if every Cauchy sequence in my space converges, then this space is said to be a complete metric space or a complete norm space. What do I mean by converges? By converges, I mean that suppose xn is a Cauchy sequence in my space X, and the limit n tending to infinity xn equals to x, then if this x also belongs to my metric space capital X, and it happens for every Cauchy sequence. So this thing is important, every Cauchy sequence, because later on when we'll deal with closed operators in quantum physics, we would see that there arises a case where a single Cauchy sequence converges, but it does not mean every Cauchy sequence converge. So the main gist of this video is, first we define what a Cauchy sequence is, okay, and then we say that, okay, what is a complete metric space? A complete metric space is in which every Cauchy sequence converges, meaning that the limit of the sequence is equals to x, and this x is itself a part of the space capital X. And now what is a Banach space? A Banach space is a complete norm space. So I discussed the idea of norm space in a previous video, and now when I complete that norm space, when I have this extra structure, see, that's the important thing. So this extra structure, that I take a norm space, okay, and there is another property that goes as follows, that all Cauchy sequences converge. then I have a Banach space. So that's the essential idea between Cauchy sequences, Banach space, and complete metric space.